All right, so we're going to talk about in this video is how to solve radical equations. So before we get into our first example, we need to take a look at what a radical equation looks like. And we're going to compare that to the graph of its inverse or its opposite, which is y equals x squared. All right, so when we go to graph a square root function, the best way to do this is just to make a quick little xy table, okay? So if we plug in 0, then the output would be the square root of 0, which is 0. So 0, 0 is on the graph. When we input 1, we take the square root of 1, and the output's 1. So we input 1, output 1. Here you go. When we input negative 1, and we take the square root of negative 1, we get an error. So we're not going to plug in any values, any negative values on the x-axis. We're only going to end up plugging in values on the positive x-axis. So then what we do is our next whole number is going to be, if we plug in 4, our next perfect square. So the square root of 4 is equal to 2. So when we go out 4 units on the x-axis, the output is 2. And what we see is it makes this little curve right here that increases very slowly. And so what I want you to notice is that when you look at a square root function, the only thing you see are positive output values only. Okay, there is no output there's no negative outputs. So when we say the square root of 16, we only define this as a positive 4. Okay, when you're talking about the square root function, the only output values for a square root is going to be the positive only. Well, what happens is sometimes when we square root, we put plus or minus, and then we mix up when we need the plus or minus and when we don't. So let's take a look over here at our quadratic function, which is the opposite of the square root function. When we go to make a table right here, we start with 0, plug in 0 squared, and the output is 0. Okay, we plug in 1, 1 squared is 1. So we move 1 unit, we output 1 unit, very similar to our square root. But with this time, when we plug in negative 1 squared, we also get 1. And so what's happening here is a negative and a positive are producing the same output. Where over here, a positive 1 and a negative 1 produced different outputs. So that is one reason to see why the difference, and sometimes we need the plus or minus and sometimes we don't. When we plug in 2 squared, we get 4, right? So we move 2 units and we go up 4. And it's not happening by mistake that the x value here becomes the y value here. That has to do with the fact that these are opposites. But what I want you to see is that when we input negative 2, then negative 2 squared is also 4. So when we're and this is therefore why we get this symmetrical parabola. When we say that x squared is equal to 16, and we square root both sides, and we're solving a parabola, that's when we say plus or minus 4, and it's going to be positive and negative 4, okay? So there's a difference in saying the square root of x is equal to 4 and saying x squared is equal to 16, okay? So maybe this will help when we're going to solve our equations as to why I sometimes use a plus or minus and I sometimes don't. It all depends on whether I'm solving a radical equation, which only has positive outputs, or I'm solving a quadratic equation, which does have positive, which can have that plus or minus. All right, so let's take a look here at the first example. And what we're going to do is we're going to solve x plus 1 is equal to the square root of 7x plus 15. And then when we're finished, we're going to check for extraneous solutions. All right. So the first thing that we need to do is we need to isolate the radical on one side, which if you look at this, it already is. The radical is already by itself on the right side of the equation. So I'm going to go ahead and copy this problem down. If the radical was not by itself, then I would use addition, subtraction, or any algebraic means to get that radical by itself. So what we're going to do here is we're going to square both sides to cancel out that radical. So the result here is going to be x plus 1 times x plus 1, and the square root cancel, and the result over here is 7x plus 15. So let's go ahead and double distribute, all right? And what's going to happen is we're going to get x squared plus 1x plus 1x plus 1 equals 7x plus 15. So we're going to subtract 7x. Oh, I'm getting ahead of myself here. Let's go ahead and combine like terms, and we get x squared plus 2x plus 1 equals 7x plus 15. All right, so now at this point, what I'm working on is I'm getting this equation written in standard form. And so I'm going to subtract the 7x from both sides. I'm going to minus the 15 from both sides, and we get x squared minus 5x minus 14 is equal to 0. From here, we may solve using square roots. We can factor quadratic formula, but I feel pretty confident that this equation is going to factor. So we're going to split the x squared, and I'm going to split the 14 into factors 7 and 2. So if we think about here, this inner and outer being 7x and 2x, though it will make a negative 5x in the middle if we make our signs be a negative 7 and a plus 2. So let's make this minus 7 plus 2. So then, as always, when we solve by factoring, we're going to set each factor equal to 0, and we're going to solve for x. So x equals 7 and x equals negative 2. But now what we need to do is we need to check our solution. So I'm going to go back to writing the original problem, just because for me it's off the page. So x plus 1 equals the square root of 7x plus 15. And so let's check our solutions, x equals 7 and x equals negative 2, and see what's going on. All right, so I'm going to plug in the 7 into this x and this x, and it's going to look like this. 7 plus 1 equals the square root of 7, and then we plug the 7 in here, plus 15. All right, so let's keep working on this. This is going to be 8 equals the square root of 49 plus 15, which is going to end up giving us 8 equals the square root of 64, which is true. Okay, now over here, I'm going to plug in negative 2. I'm going to plug in negative 2 for x. So it's negative 2 plus 1 equals the square root of 7 times negative 2 plus 15. All right, so what happens here is we get negative 1 equals the square root of negative 14 plus 15. And I can already tell you the problem. The problem is that when we're talking about a square root function, it is only defined for positive outputs. It's impossible to get this negative output. So negative 1 equals the square root of 1, and that is not defined for a radical function. So this one is going to be the extraneous. So for our final solution, we're going to say that x equals 7 and that x equals negative 2 is extraneous. All right, so I'm going to box this in, and then if you want to get your calculator, that would be great. Otherwise, you can just go ahead and take a look at this, but I want to show you a picture. So what I'm going to do is I'm going to go into the calculator, and I'm going to type in to y1 the left side of the equation x plus 1. And then what I'm going to do is I'm going to type into the right side of the equation 7x plus 15, and we're going to take a look at the graph. And the way that I was showing you here about the way the red is the radical function, now the reason it scooches off to the negatives is because of a transformation, but you can see here that the only solution is going to be right there at 7, and negative 2 is not even where it crosses. So that's a visual connection as to why you only get one solution, x equals 7. All right, so let's take a look at our next example. And what we're going to do is we're going to add in an example of rational exponents. So we're going to solve x plus 2 to the 2/3 power minus 1 equals 2. All right, so the first goal that we need to do is we need to get either the radical part or we need to get this exponent part, which is really a radical. We need to get that by itself on one side. So I'm going to add plus 1 to both sides so that we have isolated x plus 2 to the 2/3 power, and that's going to equal 3. Well, now that this is by itself, the strategy I'm going to use this time is we're going to change this to a radical. And if you recall that x to the a over b power can be written as the denominator is the root and the numerator is the exponent. So this is going to be rewritten as the cubed root of x plus 2 squared equals 3. And now I just kind of think of it as I undo the layers piece by piece. So first, to undo the cubed root, we're going to cube both sides. And so what we're left with is x plus 2 squared, because the cube and the cube root cancel, and 3 to the 3rd power is 27. Well, now I'm solving a quadratic. And this is what I want to point out to you, is this is a quadratic. And remember, when our discussion in the beginning, when we solve a quadratic and we square root both sides, okay, so let's kind of remember this. When we solve a quadratic and we square root both sides, it is defined as being plus or minus 4. And so I square root both sides, and I get x plus 2 equals plus or minus the square root of 27. So I'm going to take a step. Let's go ahead and simplify the square root of 27, which is going to split into square root of 9 and square root of 3. And so this is going to be plus or minus 3 square root of 3. And then we can minus the 2 from both sides. So in this case, we're going to get the solution. X equals negative 2 plus or minus 3 square root of 3. Okay? And this time what I'm going to do is I'm going to check my answer by looking at the graph. So let's go back into our calculator and let's type in, okay, let's go into y equals, and I'm going to type in the left side x plus 2 raised to the 2/3 power, okay? And then we've got this minus 1 right here. And over in y2, I'm going to put the right side of the equation, which was 2. And so what I'm looking for is where the graph crosses. And in this case, I can see that the graph crosses in 2 places, and therefore both of the solutions, the plus and the minus that we solved for, are both going to work. So sometimes we get an extraneous and sometimes we do not. And so I'm going to say that both of these are the solution. All right. So the last example that I'm going to do, and this one's going to be a little bit more challenging. Let's solve the equation x square root of x plus 2 plus 1 equals the square root of 3 minus x. Okay? Well, this time I think what you're going to notice is now we have 2 radicals, and I can't isolate both of them on the same side. Okay, so our goal is to isolate one of the radicals, and we have that by itself. And so what I'm going to do is I'm just going to real quick, I'm going to rewrite this problem. But now that we have this radical on the right by itself, we can square this to undo the radical, but we also need to square this side. So what happens is we have this binomial, square root of x plus 2 plus 1, times itself twice, and we're going to have to double distribute this side. But over here, we were able to successfully cancel out the radical, and we have just 3 minus x. So let's see what this is going to look like when we double distribute this right here. All right, so square root of x plus 2 times the square root of x plus 2 is going to just result in being x plus 2, right? Because what we've learned, let me come over here just as a quick note, when you take a square root and you times it by itself, the result, well, actually, let me do this. What we're doing, let me just put it right here. What we're doing is we're taking x plus square root of x plus 2 and we're multiplying itself because we're squaring it. And so the square and the square root are going to cancel and we just get x plus 2. All right, so when we take the square root of x plus 2 times 1, we just get 1 square root of x plus 2. Then I have 1 times square root of x plus 2, which again will make it square root of x plus 2. And finally, I get 1 times 1, which is going to be plus 1. All right, let's keep combining like terms. This is going to be 3 minus x. I think I wrote that wrong. Okay. So over here, I see that I have like terms. I have a 2 and I have a 1. So this is going to be x plus 2 plus 1 is 3. But I also have like terms because I have the square root of x plus 2 and the square root of x plus 2. That makes 2 square roots of x plus 2. So now what my goal is to now isolate this radical. Okay, so what we're going to do is we're going to subtract x from both sides. Let me do this in a different color. So what we're going to do is we're going to minus the x from both sides, and then I'm also going to minus the 3 from both sides. So let's see what this looks like. So these will cancel. We get 2 square root of x plus 2. 3 minus 3 cancels, and we get negative 2x. All right, so I almost have this isolated right here, but the only thing we need to do is I'm going to, in this case, I'm going to divide by 2 because of the 2 over here. So 2 divided by 2 is 1. And so what happens is we get the square root of x plus 2, and 2 divided by negative 2 makes negative x. So finally what happened is now I got the radical over on the left side isolated. So now we can again square both sides, and the result's going to be x plus 2, and negative x squared means negative x times negative x, which is going to be positive x squared. Okay, so let's work on getting this equation in standard form. I'm going to actually leave the x squared right here, and I'm going to subtract the x over here, and then we're going to minus the 2 over here. Okay, so the result's going to be x squared minus x minus 2 equals 0. And I think this is worth to see if it factors. So let's see if we can split this. If it didn't factor, I would use the quadratic formula. So we're going to get x minus 2 plus 1, and it does in fact factor. So x plus 1 equals 0, x minus 2 equals 0, and we get x equals negative 1 and x equals 2. Okay? So there's a couple different ways that we can check our answer. We could take the answer and we could plug it back in. Okay? So maybe we choose to do this, or maybe we choose to look at the graph. So let's say that we check. Now what I need to do is I need to rewrite the original problem back here. Plus 1 equals the square root of 3 minus x. And we're going to plug in both of our answers. So I'm going to check x equals negative 1, and we're going to check x equals 2. So let's plug this in. This is the square root of negative 1 plus 2 plus 1 equals the square root of 3 minus, and then we're going to replace this with a negative 1. All right, so negative 2 plus 1 is 1. Plus 1 equals the square root of 3 plus 1, which is 4. So 1 plus 1 is equal to the square root of 4. 2 is equal to the square root of 4, and I feel pretty confident that this is true. Okay? Well, now let's plug in our other solution. This is going to be the square root of 2 plus 2 plus 1 equals the square root of 3 minus, and what I'm doing is I'm plugging in the 2 in for both of these x's, right? So I plugged it in for this x and this x. Now let's kind of work this out and see what's going on. The square root of 2 plus 2 is 4 plus 1, and that equals 3 minus 2, which is 1. So square root of 4 is 2, square root of 1 is 1, and what we see is this says that 3 equals 1, which is not true. Okay, so it's pretty clear to see. Now the other way that we could have checked our answer is to go into the calculator, and we could have also gone into y equals, okay? And I'm going to type in the left side of the equation, which was x plus 2 plus 1, and then down in y2, we're going to type in the right side of the equation, 3 minus x. And when I hit graph, we can see what our solutions are. And when I look at this, I see that the only solution is right here at negative 1. Okay, so that's another really nice visual way to check your solutions without having to plug it back in, okay, if you find that process to be a little bit tedious. So let's wrap this up here. The solution is going to be x equals -1, where x equals 2 is extraneous. All right, so that is the basics of solving radical equations. And obviously there's more types of equations that I haven't even shown you yet, so it just takes a lot of practice to get good at this concept. All right, thanks for watching. Bye.